I'm the work package leader, I guess I have to have a short introduction to the work package. This is work package 4 that we're going to be discussing now. And there are 4 participants. We have slightly different amounts of personal months which are being budgeted. KIT, ANFUS, VTT in Finland, and Kamakta. The objectives, I don't know if I really need to go into detail with these because I think we've been doing these exercises long enough now that everyone knows what we're talking about. But basically, we want to model sorption in a way which will reduce uncertainties in the PA. So that's basically a 4-point process: identifying key processes, developing models for the processes, identifying and characterizing main sources of uncertainty, and then, of course, testing consistency between different modeling approaches, and some of which may be applicable to small scale, others for large scale. So the 4 presentations that you're going to hear now, I'll start with my own approaches to modeling surface complexation on complex materials with limited data. Then I'll introduce the other work package participants. So, approaches to modeling surface complexation sorption on complex geological materials with limited data. I think I'll start by having a disclaimer. This presentation contains material that some people here might find provocative. It's basically a first attempt for me to flesh out some outlandish ideas that I've been playing around with for dealing with very sparse sorption data sets that were never really intended for the purpose of sorption modeling. And of course there are many uncertainties, not all of which I'm going to mention, but those of you here who have worked with sorption models before will know exactly what they are. And it's still very much a work in progress. So to begin with, I thought I'd give an example of what the normal workflow would be in a traditional approach to surface complexation modeling. And for this purpose, I use sodium illite as an example. And I've basically taken some synthetic data because I didn't have any real experimental data to work with. So basically, you start off with a set of measurements. And this is what you would commonly call a pH sorption edge, basically correlating the sorptivity of the solute, in this case europium, against the pH of the contacting solution. Now, the process then, traditionally what you would do is successively fit different reactions for different surface complexes, and eventually you end up with something that explains the overall sorption over that entire range of pH you've examined. And sometimes you may choose to neglect certain processes such as cation exchange at low pH if your focus is very much in the neutral to basic range. That is, of course, is very much dependent on what solute you're working with. Some are more sensitive than others. And basically you end up with a whole lot of equilibrium constants for these reactions. Now, one of the uncertainties that I think a number of you might already have noticed is that some of these proposed surface species are probably, well, they're uncertain. Some of them may not even exist. This is basically a curve fitting exercise. Particularly when you come up to some of the higher hydrolysis steps, there's very, very little to suggest that these species exist at all. But sometimes you may need them to fit the data set. That may be because of the underlying thermodynamic data that you're using in the speciation modeling forces you to make these choices that introduce uncertainties. But if we look beyond that for a moment, what you can do is that you can generate something called a linear free energy relationship. And these are empirical relations, and they're quite common in aquatic chemistry. And they're used to describe correlations between paired sets of very, very closely related data. In this case, surface complexation, at least the way that we model it, the reactions are very, very similar to aqueous phase hydrolysis reactions. As you can see here, we have a surface complexation reaction and a hydrolysis reaction. And the main difference is that an immobile surface group takes the place of one of the water molecules in the reaction. So there's a very strong chemical analogy there that we're using. And of course, if you have enough data sets based upon fitting parameters for different solutes, you can find a correlation between the hydrolysis reaction constants and the fitted surface complexation binding constants. So in the case of the illite example, you can collect data from a bunch of different solutes, put them together, do a linear regression, and you get something that looks like this. This actual curve was developed by Bradbury and Bynes at PSI, and I think it's quite a remarkable piece of work because it shows the chemical consistency of this geochemical analogy over something like 35 orders of magnitude, which is really big, this being a log scale, of course. There are further examples of these relationships in the literature for different minerals. I've plotted a few of them here. The one for silica was never actually stated outright that there was an LFER in the literature source. I reinterpreted that from their report on binding constants. But basically, they all tell a very similar story. There's a chemical consistency between reactions which occur in the aqueous phase and what you could call analogous reactions which occur on surfaces. So why are these important? The main reason is that it's generally not possible to make sorption experiments on all the solutes if you'd really like to be able to study in PA, particularly when you have equilibration times for these materials that may extend to many months, sometimes even years. In the case of the SKB site investigation data, a small subset of nuclides was chosen to represent broad chemical trends. You have some surface complexing solutes, you have some redox sensitive solutes, you have cation exchanges. And these LFERs provide a means for estimating reaction binding constants where there are no experimental data. But then the big disadvantage of this is that it's highly dependent upon the consistency and accuracy of the thermodynamic data that you're using for the modeling. So our modeling approach is based upon the prior assumption that there should be a linear free energy relation for sorption on the mineral surfaces. And we use that as an underlying construct in the modeling rather than focusing on the binding constants themselves. And then the idea is to look at the literature data for single mineral systems and use this as a basis for building a generalized bottom-up sorption model which can explain sorption processes on more complex mineral assemblages. And the first 2 points are not particularly new, but the third point here, I thought it would be very interesting to look at what properties do these LFERs give to the system that might perhaps allow you to make some mathematical simplifications. So the first question, how does the intercept of the free energy relation affect sorption. Basically what happens is that it has the same influence on all sorbing solutes. And in this case, I have the example of the different hypothetical surface species formed of europium. And you see that the basic effect is that you scale the net KD up and down. All the reactions are affected in a similar proportional manner. Now, what happens if you normalize that curve? Because all the species are affected identically, if I normalize that curve relative to a given pH level, or perhaps the KD of another solute, I find that the curves, in a relative sense, are stationary. You still have a relative variation in KD as a function of pH, but now you get away from this problem with the absolute value of the KD. How does the slope of the free energy relation affect the sorption? This is a little bit different. What it does is that it alters the relative contribution that these different species make to the overall sorption that you measure. And you see that minerals with low slope factors, such as quartz and, well, there's a bunch of different minerals that I haven't actually investigated, but you find that they are theoretically more strongly influenced by some of these hypothetical higher hydrolysis steps than perhaps minerals with a very high slope, like ferric oxyhydroxides, in which case you may only need one, the first binding constant, to give a pretty good description of sorption over the entire envelope of the pH dependency. So how does this help? Here I've just given a definition of how I would go about defining the KD in the context of a surface complexation model. So you have some parameters which depend upon site density and surface area. You have some parameters which depend upon aqueous phase speciation. You have also something to do with the reactivity of the surface, the charging model that you have. Then also you have the scaling factor due to the intercept, the scaling factor which is related to the reactive surface area, and then of course the slope factor and the hydrolysis constants. And by looking at this equation, it's very, very easy to see that there's some redundancy in some of the parameters. Basically, the surface area fractions and the intercepts of these free energy relations are somewhat redundant. And you could replace them with a single weighting parameter for each reactive surface that you could then set about fitting to macroscopic sorption data. So this is the data that we actually have from the site investigations for, in this case, americium. We have two different saline compositions for Laxamar and Forsmark. We have a meteoric groundwater composition, which we've done sorption studies for both Laxamar and Forsmark. Then there's a marine groundwater composition and a brine groundwater composition. And this is for a crushed size fraction of 1 to 2 millimeters and a contact time of between 160 and 180 days. It differed a little bit. So basically, the big problem we see here almost immediately is the fact that we have a very sparse data set. At best, for each groundwater composition, we have one pH level that we're investigating. So the big problem is, how do you use this data to constrain a surface complexation model? Because we don't have this nice sorption edge that you can do with clay minerals and you can do with oxide minerals and have very, very fast equilibration times. So this is americium. Slightly different curve for europium. Somewhat surprisingly, because europium and americium are often taken to be good geochemical analogues of each other. This may be due to experimental biases of different kinds, I don't know. Haven't really got to the bottom of what that might be. Some of it may be related to the thermodynamics of the different solutes. But then nickel has a very, very different chemistry. it is sensitive to pH because it forms surface complexes. But then also we know that nickel is also affected by ionic strength. It forms cation, well, it does cation exchange. And you can see here that the fresh groundwater compositions are associated with high pH levels, and the very saline compositions are associated with low KD. This data set is very complex to analyze because you have pH dependency and then you have an inverse correlation with ionic strength. So you're seeing effects of both surface complexation and ion exchange. So the modeling strategy that I've adopted is, it's actually a hybrid of what they call bottom-up and top-down modeling approaches. And because no presentation will be complete unless you coin a completely new term, I've decided to call it the bootstrapped component additivity model. So the basic idea is to assume a mix of at least 3 minerals with a broad spread of slope factors to capture the overall sorptive trends, even if you don't account for the full mineralogy of the system. So in this case, as a first approximation, I say, okay, let's go with quartz. There's about 35% quartz in the system. Then I've taken illite because I have data for it, but then I think that it may be a reasonable geochemical analog for biotite, which is an important mineral as we've seen today already in the sorption in granitic systems. And then, of course, we have hydrospheric oxide, which only exists in really, really small amounts in the rock, but it has a disproportionate effect on sorption because it binds things very strongly. And it has a big surface area. So the procedure I've adopted is to attempt to find a set of positive weights that will give the best simultaneous fit to americium, europium, and nickel KD data for the Forschmark metagranite in contact with the saline groundwater. And I only chose the saline groundwater. Well, actually, there was 2 reasons I chose the saline groundwater. First was that it had the best statistical representativity. I think there were 5 samples times 3 replicates, so 15 measurements that I could base the mean behavior of the rock on. And then also the fact that because it's strongly saline, it will minimize the effect of cation exchange in the case of nickel. So I'm trying to isolate the component that is associated with the surface complexation. And by focusing on the saline groundwater, I try and minimize the effect of the cation exchange. So it's no point fitting weights if you can't test the model. So the test is to make predictions of KD for the fresh groundwater type, and then to compare the model predictions with the actual measurement data. And that, it's definitely not a proof, but it's a good test of model skill, to see if the model can actually reproduce the data. So here's some results for americium-3. We have the saline data, which we fitted, and the model prediction for the fresh groundwater. The lines that you see are more or less titration curves for altering the partial pressure of carbon dioxide in the system. Because that was not measured, we don't know what that was. But we do know that there was a pH drift from the initial composition of the groundwaters as they are defined, and then the equilibrium compositions. And because we see exactly the same pH drift in the control samples, which had no geological material, we have a pretty good reason to believe that that may be related to a partial re-equilibration of these samples with a lower carbon dioxide partial pressure in the fume hoods. And there's a little bit of difference between the saline and the fresh groundwater, but they end up being something like 10 ppm carbon dioxide. Of course, the fitted parameter, the fitted data is exact because we're fitting it, but then the model prediction slightly underpredicts what you actually see for the americium. These are the results for europium. Once again, I have the fitted data and the model prediction. This is also a very good prediction. It matches the measurement data very, very well. The results for nickel. Same procedure. Fitted data, model prediction. In this case, though, we see that the nickel KD is slightly under. Well, it's at the lower edge of the confidence interval for the measurement. And that's actually consistent with the fact that you've neglected cation exchange in the case of nickel, because cation exchange will be much more prominent in the fresh groundwater composition. So you would expect that to function as an extra sorption process to give you a slightly higher KD. So the conclusions of this work, I'm trying to be very careful, not make too extravagant claims, but I think that the approach, it seems promising. So far I've only looked at a very limited data set, but the thing is we really need to develop new modelling approaches to try and handle these data sets which are limited by their very nature. It's just not possible to create sorption edges, I don't think, for such complex materials which have long equilibration times. Well suited to limited data sets, as I said. However, there are problems. Basically, this is a problem for all sorption modelling approaches. It's impossible to prove these sorption mechanisms, the different surface species that are presented, because basically they're hypothetical fits to the data. The only way you can really prove it is by confirming the existence of the surface species with spectroscopic data of various kinds. And I think at KIT you've done quite a lot of work with curium, I believe, for surface speciation. So they're the kind of experimental techniques that you need to be able to say whether the model is realistic or whether you're just fitting a data set. Another really big problem is the fact that the predictions are very highly sensitive to the quality and consistency of the underlying thermodynamic data. And that's particularly in the basic pH range. And that's not only to do with the actual numerical value of hydrolysis constants and so forth in your thermodynamic database. Perhaps more importantly, it extends to the whole question of whether some of these specific hydrolysis reactions which actually exist in the thermodynamic databases exist in reality, or whether we just think that they do. Everything that you model with a database that is incorrect will have a bias introduced because of that. So, future work, basically I would like to show that the results that we got for the Forschmark data aren't a fluke, and we can perhaps reproduce the analysis for the Esper and Laxamar data, and also the perhaps some of the measurement data which comes out of work package 2. That would be very nice to do in the future. And then also an uncertainty which I haven't mentioned yet, but I could do an entire new presentation on if I needed to, is possible bias due to diffusive disequilibrium. Solutes that sorb differently in terms of their KD will also diffuse differently. So you'll have some solutes will be more equilibrated than others, which will give you a bias in your estimation of weights fitting the system. And that's even after 180 days. The data clearly show no sign of any sort of plateau, which, yeah, it's difficult to know how much longer you would need to carry out these experiments to see when you actually got an equilibrium state. And I thought I'd finish off with a little cartoon, which, by way of apologizing for my use of log scale in every picture, this also highlights a pretty important point, that when you do analyses in log scale, things that seem to have a very, very small deviation in log scale blow up to be massive differences in a linear scale. So that's something to be aware of as well when using things like these linear free energy relations. So thank you for listening. And I might point out that I've already created a hashtag for the CROCK on Twitter. Much to my disappointment, I find that most people using this hashtag have a completely different meaning for CROCK, which I talked about last year. So thank you very much.
Yeah. Questions, comments? Yeah.
Be careful with your friends in Twitter.
I'm sorry?
There is a joke about the friends in Twitter you can do with this CROCK hashtag. But the question is that I think one of the critical steps is the calibration or fitting of these weights.
Yes.
So my question, from a practical point of view, is in this application you did it by trial and error or a kind of optimization algorithm?
Yeah. In this particular case, I had 3 solutes, and I had 3 measurement points, and then I had 3 minerals. So basically, I could get an exact match.
Yes.
If you had more solutes, or perhaps you had 2 pH levels, you could do a fit in a least squares sense, which would be perhaps would give you a lot more confidence. As I said, this is a work in progress, and you know, a fit on 3 data points is not really very convincing. But it's mostly to demonstrate perhaps there are different ways of doing the surface complexation modeling that we don't normally do.
No, in that direction, I cannot really evaluate the major underlying assumption of the chemical underlying assumption is that parallelism of these 2 processes. So I leave that for chemists, so
yes.
I cannot do.
Yeah.
But from a numerical point of view, I think something important for the future, if it works, I think is very promising, but when you have more data, I think something critical would be the uniqueness of the solution, because then the amount of slopes and weights that you can fit, in that sense, lose a little bit the mechanistic view of the very beginning, that we wanted to be more mechanistic and less
yeah.
What do you think of?
I think even if you can't really use this method to get reliable models that you could use in PA, on the other hand, you can use it to test assumptions in the modeling. For example, if I go back to, let's say, americium, going from a KD of this magnitude in the saline to a KD of this magnitude in contact with fresh water is telling you a lot about the competition between speciation reactions in the solution and what's actually going on in the surface. Now, I used hydrolysis reactions in the aqueous phase. I also used carbonate complexation reactions in the aqueous phase. We know that americium and europium form complexes with silicate as well. And in the saline groundwater, actually, you find, if you use the thermodynamic constants from the SKB database, pretty much everything is in the form of a silicate complex. And what that does is that if you try and fit the model to that measurement point, assuming silicate complexation, you're introducing a very, very strong bias into your model that has a consequence when you extrapolate. Now, when you extrapolate to the fresh groundwater, if you have this silicate complexation in, you find that the silicate depresses the sorption of the KD so much in the saline case that you would model a much higher KD for the fresh groundwater. So straight away there, you see there's something suspicious about the thermodynamic constants for the silicate complexations. I'm not sure exactly what they are, if they're overestimated or perhaps, yeah, I don't know, perhaps one of the chemists who deal with this every day might be able to give a better explanation. But the modeling assumptions, and including the assumptions in the thermodynamic database, which gives you your speciation, that has consequences when you make predictions. And if the predictions very obviously don't match the measurement data, then you can tell that diagnostically there's something strange with your understanding of the system. In fact, in many respects, that might be better than if you get an exact match. If you get an exact match, it doesn't really tell you anything interesting. If it tells you something you weren't expecting, then obviously you have a conceptual problem somewhere.
Yeah, Ignacio.
In your first graph, can you show the first graph?
Yeah.
Perhaps it's
My synthetic data.
You know, I think it was. Yeah, here, for example, or whatever. This is not the first one, but.
The trouble with animation is that it takes a lot of clicking to go back through it. This one.
This one is not really simple, but perhaps it's a silly thing. In the y-axis, you have KD divided by KD0. What is KD0?
It's basically just a reference level, because I didn't want to focus on the absolute value of KD, because someone might look at it and say, well, illite obviously doesn't sorb that strongly or that weakly. I say, okay, I'll make some point my zero level, which I think was pH 80. Not entirely sure, but
yeah, now I see that it says synthetic data. I thought looking at these points that the points were real. That's why I was confused.
yeah, basically I simulated the illite model which Bradbury and Bynes produced, and then I added a little bit of Gaussian noise just for fun. Because I didn't have access to a pure data set myself, and I didn't have time to start refitting models. So, yeah. This is just by way of an example.
Yes,
not,
I understand now. I was looking at the points, I thought these were real points, and that's why I was. Okay.
The thing is, what I tried to illustrate is the fact that you do have a lot of uncertainty in these data points, particularly when you get up to the higher pH levels, and you may not even need some of these dubious surface reactions. And I know Thomas doesn't like this one in particular.
But only this. The other ones, you have some spectroscopic indications that the other species are really reasonable, very reasonable. Yeah.
I think you could probably lose this one in its entirety, and you would probably still match the data reasonably well with the noise.
Yeah. I mean, most pH electrodes don't work very well at these levels of hydrogen ion concentration. So already there you have an uncertainty about is the pH really well?
Yeah. And not only that, the surfaces themselves become unstable. They may start to dissolve, turn into different things, zeolite or whatever.
Okay, maybe I have a question. Maybe you can show once again one of your last slides for your americium and europium absorption modeling.
It might be easier if I just go through them like this.
So in principle, if you're in the alkaline pH range, you are always in the saturation range of absorption. Yeah, you have some saturation. But based on your, let's say, americium absorption data, or your maybe go back one to americium. Okay. Here you have in the alkaline range with a short pH range a very steep increase of absorption. Right? But we are for sure away from the absorption edge. Yeah. And for europium, for instance, you have a much the slope is strongly reduced if you go to europium, and the behavior of europium and americium, maybe they are not 100% identical, but should be similar.
I don't like to call these.
Here you go into the saturation, yeah.
Yeah, I don't like to call the titration with carbonate to be a pH edge, because the carbonate has such a big influence on the speciation, the solution, that you know, if you were to do the same thing by adding hydrochloric acid or sodium hydroxide, you may get a very, very different kind of sorption edge.
I think for the trivalent, the carbonate influence is not as big as, for instance, for the radium-6, yeah. And also, especially for illite, there are some data in carbonate, in presence and absence of carbonate. And from the sorption data, there's not a very big difference. Okay, for the modeling, you have to include also some carbonate surface species. But I have a problem if you have a very steep slope, even in the alkaline pH range. And of course, if you have only 2 points, then you need 2-3 points more to validate your prediction. Otherwise, this is, well.
Yeah, I think ideally you'd like to have at least 3 very different surface complexes that have chemistry that are well understood, and then ideally 2 or 3 pH points, given that you'll never have a complete pH sorption edge the way that you'd like. The more points you have, of course, the more, perhaps the more reliable the fit would be.
And in fact, for me, it was not absolutely clear what are the parameters you have fitted. Have you summarized?
Here I just fit the weights of the relative amounts of each mineral.
That is the only parameter you fit.
Yeah, but I've combined it with the intercept of the free energy relation. And the reason why I do that, actually, I didn't mention either, is because a lot of the studies on the pure minerals, the pure mineral phases which are used in the experimental investigations are nothing like the mineral phases you have in the real rock. For example, silica. Experiments are normally done with silica gel, or at least the data I had access to, and that probably has very, very different surface properties to quartz. And I don't know about hydrospheric oxide, but I can imagine that may be quite different in the rock matrix formed naturally than what you would create in a laboratory. So I think there's a lot of uncertainty in these free energy relations, particularly in the intercept. The slope also has a considerable amount of uncertainty in it as well, but I think if you can remove at least one of those parameters, then you're doing a lot better, because you're in the business of compounding all these different uncertainties along the way. And if the fundamental model that you're using, underlying everything, already has an order or 2 of magnitude error in it before you've even started working out the relative proportions of minerals, you've got no hope of having a PA quality model of surface complexation. So if you can combine these parameters together in some way to remove the unnecessary uncertainties, I think that's probably a good thing.
Okay, more questions? If not, we go. Thanks again, and we go on with the